So here in Lecture 8, we're going to complete our overall study of multi-level logic synthesis by looking at don't cares. Now, don't cares are probably familiar to you from just basic logic design. In basic logic design, we said for some pieces of logic, some inputs just won't happen because of something you know about the surrounding context or the usage of that hardware. And so you are free to decide whether the hardware design that you're making makes a 1 for the output when that input shows up, or it makes a 0. And it lets you actually optimize things in a more rich and flexible way. Well, the same thing is true for multi-level logic networks, but a new and very important thing happens. Don't cares simply arise naturally and organically and implicitly inside one of the logic networks that we're working on as a consequence of the Boolean logic network model, as a consequence of the algebraic model for the nodes. They just happen. Not only do they just happen, they happen a lot. They happen all over the place. They are a rich source of optimization for our logic, but the new and interesting challenge is you've got to go hunt for them. Turns out, all the computational Boolean algebra techniques that we taught at the beginning of the class are exactly what you need to go find them. So in this starting lecture, what we're going to go do is walk through a nice and interesting example to show you how these don't cares just implicitly arise in the networks that we're studying. So let's go take a look.
So let's start our discussion of how don't cares show up in multi-level logic with a little bit of background. So let's recall that we made progress on multi-level logic by simplifying the model. The algebraic model really gets rid of a lot of the difficult Boolean behaviors to let us do things like division and factor extraction. But we lose some of the optimality, some of the result quality, some of the expressivity of the model in the process. So an interesting question is how you get it back. And one of the surprising answers is don't cares. So recall that we run an espresso-style simplification on the two-level sum of products form in each node of a Boolean logic network. And to help this, what's going to turn out to be the case is that we extract don't cares from the surrounding logic, and then we use them inside each node. And the big difference in multi-level logic is that the don't cares just happen. They are a natural byproduct of the Boolean network model, and so there's a word for that. This is the title of this lecture. They're called implicit don't cares because they just happen as a natural consequence of the structure of the graph for the Boolean network model. So they're all over the place. In fact, there are lots of them, and they're very, very useful for simplification, but they're not explicit. And so the new thing is that we have to go hunt for them. We need computational procedures to find them. So let's just review a little bit about don't cares first. In basic digital design, you probably learned this about don't cares. And what we said was that a don't care was an input pattern that can never happen. So I've got a little logic function here, a little gray box. F has inputs A, B, C, D, and I've got a Carnot map shown on the right-hand side. 2 by 2, AB on the horizontal axis, CD on the vertical axis. This Carnot map has ones in the ABCD 1000, 1001, and 0111 squares. But it's also got a bunch of D's in it, and the D's are don't cares. And so what if we just tell you that the following patterns of ABCD cannot happen? 1010, 1111, here I'm just going to check them now, 1100, 1101, 1110, 1111. What if we tell you that those things cannot happen? Then each of those things can become a don't care in the Carnot map, and we get don't cares in 1, 2, 3, 4, 5, 6 places corresponding to those patterns. And so we're free to decide if F is a 0 or F is a 1 here because those things don't happen. That output is not going to happen, so we get to decide what the function should do to simplify things. And it's clear that we can simplify things much further. With all these don't cares, I can circle some nice big circles in the Carnot map. So that's probably what you know about don't cares so far. What's different in the multi-level model? Well, don't cares arise implicitly as a result of the Boolean logic network structure, and you have to go find them. We actually have to go search for them explicitly. They don't just get handed to us like that previous slide. There's a bunch of good references for these ideas. The Nani DiMichele book on synthesis and optimization of digital circuits is good. Some of my development is based on some of the ideas in Chapter 8, though I'm doing a sort of a different version of the math. The book by Devadas, Koitzer, and Ghosh on logic synthesis is also good. And there's a very complete paper by a lot of authors, Bartlett, Brayton, Hechtel, Jacoby, Morrison, Rudell, Sanjivani, Vincentelli, and Wang on implicit don't cares. That's a good place if you want to see how it really works. So let's do a sort of an informal tour of how multi-level don't cares arise implicitly in the structure of the Boolean network model. And let's start with this little Boolean network, and let's look at the node called f. This is a very simple Boolean network. It's got one node, f equals xb plus by plus xy. And the question I would ask is, can I tell you anything just looking at this network about the don't cares in the node? And the answer is no. I don't know any context for the surrounding parts of the network. I cannot tell you that any patterns of x, b, and y are impossible. So as far as you know, all 8 of the patterns of x, b, and y are possible. And there's a little Carnot map shown at the right, 4 squares by 2 squares, xb on the horizontal axis, y on the vertical axis. And there's 3 groups of 1 circled, the xb pair, the by pair, and the xy pair. So what changes here? Well, suppose we know something about the input. In particular, suppose we know that x is not an input from the outside. Suppose we know that x is computed inside the Boolean network. So just to be clear, I'm labeling PIs as the primary inputs, things that come into the overall Boolean network, and POs as primary output, things that leave the overall network. And so now x is not a primary input, it's a computed thing inside the network. Now can I say something about whether there are any impossible patterns for the inputs to node f? And the answer is yes. Because there are some relationships between a and b and x now, some things just can't happen because x is a function of a and b. There are now some impossible patterns of the variables x and b and y. So let's just go look at those. So I'm showing again my Boolean network model with the x equals AB node connected to the f equals xb plus by plus xy node. And I've got a little truth table here with the x equals AB node pointing at it. And it's got 3 columns, a, b, x, and under it all of the Boolean values of a, b, and x from 0, 0, 0 to 1, 1, 1. So there's 8 rows. And then there's another column that says, can it occur? And what we're really asking here is, inside this logic network, now that we know that x is a, b, can each of these 8 patterns of a and b and x actually occur? And so the first thing that we can do is just say, well, 4 of them can certainly occur because x is equal to a and b. So the patterns associated with x equals to a and b can occur. So 0, 0, 0 can occur, 0, 1, 0 can occur, 1, 0, 0 can occur, and 1, 1, 1 can occur. So we have yeses in all of those rows. So it would seem that all of the other rows are no's, and yeah, that's actually correct. There are 4 patterns that cannot happen to a, b, and x, 0, 0, 1, 0, 1, 1, 101, and 110. And we can illustrate one of those clearly by just pointing at one of the rows. So let's point at the 0, 0, 1 row and say, well, why is it that that cannot occur? And the answer is, well, a and b are zeros, and x is an AND gate output. You can't put 2 zeros into an AND gate and have a 1 come out. So that's just not possible. So here's all the possible and impossible patterns for a and b and x. Now, however, I'm not that interested in the patterns of a and b and x. I'm interested in the patterns of x and b and y, because that's actually what f is a function of. I need to figure out how I can take the abx patterns, and I know something about what can't happen, and turn those things into x, b, y patterns. And all I can tell you at this point is you just have to sort of stare at things. We're going to figure out computationally how to do this in a bit. So the first thing is that there are 3 pairs of rows. The rows that start 0, 0, the rows that start 0, 1, and the rows that start 1, 1 in this table of x, b, y, 8 rows patterns. Because look, y, as far as we know, is a primary input. It just, it's not dependent on anything. So y can be anything. But x and b are dependent on each other. And the xb00 pattern can happen. The xb01 pattern can happen. And the xb11 pattern can happen. And so that would seem to suggest that these 2 rows, xby is 100 and 101, cannot happen, and that's actually correct. And why that can't happen is that this is trying to put b equals 0 in to what is actually an AND gate and get x equals 1 out. You don't put a 0 in an AND gate and get a 1 out. A 0 cannot go into the x node and have a 1 come out. So any of the patterns that have x is 1 and b is 0 are impossible. And so we found a couple of impossible patterns for our F node. And so we can use those things. We can check in our Carnot map, which I've got drawn here again, for the xb versus y, 4 variables horizontally, 2 variables vertically. I've got the same Carnot map drawn with the same 3 terms, xb, bx, xy. And now I'm going to say, well, what happens if we add the impossible patterns? And the answer is we have 2 impossible patterns. xby is 1, 0, 0 and 1, 0, 1. And I get 2 don't cares. The entire right column of the Carnot map, 100 and 101, are now don't cares. And suddenly, I can circle the Carnot map in a different way. I can circle this in what I think is a nicer solution. If I'm going to write the function now, I have that the function is equal to x plus by. And that's simpler than xb plus by plus xy. And so it looks like I've saved something. So I can actually simplify this network. It is no longer xb plus by plus xy. It's now x plus by. It looks like I saved 3 literals. And I actually saved a product term. This is actually really good. So just because of the context of how x is a function of a and b, there are patterns of x and b and y that cannot happen. So we can continue this and just try another one. Now what happens if y is also a pattern? What happens if y is b plus c? It's again computed internally. We can do this again. We can say, are there impossible patterns of the inputs and outputs of the y node of b and c and y? And so I've got another truth table here that has 3 columns b, c, y with 8 rows from 0, 0, 0 to 1, 1, 1. And the column to the right says, can it occur? And you start just like before with the patterns that can occur. You can send 2 zeros into an OR gate and have a 0 come out. So the 0, 0, 0 row is a yes. If you send any 1 in to an OR gate, you get a 1 out. So the 0, 1, 1, 1, 0, 1, and 1, 1, 0 rows for B, C, Y are a yes, which leaves the other 4 rows as a no. 0, 0, 1, 0, 1, 0, 1, 0, 0, and 1, 1, 0 cannot happen. And we can just draw those to be sort of clear. The 0, 0, 1 row says you cannot put 2 zeros into an OR gate and have a 1 come out. That's not possible. And the 1, 1, 0 row says, similarly, you can't put 2 1s into an OR gate and have a 0 come out. All 4 of the rows in this truth table are impossible because they're just not legitimate patterns of inputs and outputs for the Y node in this network. So now we can take all of the information we've got, and I'll admit a rather complicated looking slide here. So I've got the logic network again, x equals AB node, y equals B plus C node, feeding the f equals XB plus BY plus XY node. And I've got the impossible patterns for ABX again drawn above it, 0, 0, 1, 0, 1, 1, 101, 110. And I've got the newly found impossible patterns of BCY drawn above it, 0, 0, 1, 0, 1, 0, 100, 110. And I've got another truth table, XBY, 8 rows, 0, 0, 0 to 1, 1, 1, and another column that says, can it occur? And just as before, I don't really want the ABX impossible patterns and the BCY impossible patterns. I want impossible patterns I can do something with, that I can use to create maybe some don't cares for the F node. And so right now, you have no computational technique for doing this other than to stare at this and try to figure out what can and can't happen. So the first thing you do is you say, all right, look, I stare at it and I believe that XBY is 0, 0, 0, 0, 0, 1, 0, 1, 1, and 1, 1, 1 can happen. And if you just try all those patterns on your x equals AB and y equals B plus C nodes, you'll see that you can find other values for the inputs not specified, in this case A and C, that make that work. And so that leaves us with these 4 patterns, 0, 1, 0, 1, 0, 0, 1, 0, 1, 1, 1, 0 for XBY as impossible. And we can again look at them Why is 0, 1, 0 an impossible pattern for x, b, y? Because you're trying to put a 1 in an OR gate and get a 0 out. Why is 1, 1, 0 impossible? Because you're trying to put a 1 in an OR gate and get a 0 out. Why are the two patterns 1, 0, 0 and 1, 0, 1 impossible? Because you're trying to put a 0 in an AND gate and get a 1 out. Because of the context of this network of what x is as a function of a and b, and what y is as a function of b and c, certain patterns of x and b and y are impossible jointly. And these things become don't cares. And so we get some more good stuff. Okay, so if we take these impossible patterns, and so I'm drawing the Boolean network again, x is a, b, y is b plus c, f is xb plus by plus xy. I'm drawing the impossible patterns above the x, b, y inputs to f, 0, 1, 0, 1, 0, 0, 1, 0, 1, 1, 1, 0 for x, b, and y. Those are impossible. I've now got 4 don't cares that I can use. And what I actually get is 2 new don't cares. I get a don't care for the xby 0, 1, 0, and I get a don't care for the xby 1, 1, 1. So in this Carnot map, 4 columns wide by 2 rows deep, only the xb00 column has zeros in it. Everything else has a don't care or a 1 in it. So if I was to circle this Carnot map, I'd just circle this. I'd circle the 2 middle columns. And if I write this as a Boolean equation, this is now f equals b. And that's pretty surprising because that means that I don't really care about the x node and I don't really care about the y node. I only really care about the b primary input just because of the context of x and y now being related because they share some variables. And I don't even have to circle one of those previous ones in this Carnot map, right? Because it's become a don't care because of this context. And so, wow, f was xb plus by plus xy. That looks like 3 AND gates and an OR gate with 3 inputs. And that whole thing gets replaced by a wire. Wow, that's pretty surprising. That's pretty impressive. And so this is just the first start of our examples for how we find don't cares. This is one kind of a don't care. These are actually things called satisfiability don't cares and controllability don't cares, but these aren't the only kinds. There's actually some more kinds. So in the next lecture, we're going to look at some other implicit don't cares that we can pull out of this network.